Thank you very much. And I just flashed my background just to let everybody clear that this is going to be an experimental talk. Okay, so ultracold atoms, optical quasicrystals. I forgot that I added a second part to the title, but the content is going to be the same. This is experimental work done in my group in Cambridge, mostly by a couple of brilliant PhD students, amongst them Konrad, who is now on ETH in Zurich since last week, and Matteo, who's actually somewhere here in the audience. And you can pass to him with all of the detailed questions later on. And Ed, Ju-Chin, and Choria are like younger PhD students that started later on. And of course, we're obviously always looking for great people to join our team. Right. Why should I think about quasicrystals? Why should that be interesting? And the answer is, in some sense, very fundamental, I believe. The answer is that what we're doing is we're playing with reasonably complex quantum systems and we try to understand them as best as we can. What will we do when we have done that? What will we do when we have understood everything there is to be understood about Hubbard models and simple lattices and all of that? That's admittedly quite some time into the future, but what we want to do is we want to increase the complexity of the systems we do. And if you believe in quantum information, quantum computing, you just say, I have to increase my system size, and then stuff will become automatically more complex. If you have a condensed matter background, on the other hand, you would say, actually, no, that's not really true. This will stop at some point. If I think of like 5 lattice sites, 10 lattice sites, 100 lattice sites, yes, complexity is increasing, but at some point, complexity becomes constant. And that's the regime where, like in an RG idea, we say we have a scaling approach, where just it gets more of the same. We are maybe close to the thermodynamic limit, not much is happening anymore. And that's the regime where the length scales you're now considering are much, much bigger than all relevant length scales. Or saying it another way around, if you can simulate 1 liter of water, simulating 2 or 5 liters of water is not exponentially harder, because there's just nothing new coming in that scales. So what we want, therefore, if we want to make our quantum systems more and more and more complex, then we want maybe have a quantum system with a non-trivial structure at all length scales. And you can see some of the scalings of this already playing out in condensed matter physics. Like all of the elemental materials, the elemental metals, 1 atom per unit cell we understand reasonably well. If you think of the YBCO crystal Christian showed in the beginning of his talk, that's already much more complex because we have like 50 atoms or so per unit cell or up to. So if we want to get more complex, we want to have more length scales. There's of course a whole industry in how we can do this in cold atoms. We can say, let's have competing interactions, works, put the system in cavity, maybe multi-mode cavities. We can add length scales one by one from the outside world. But there's maybe another, maybe better way of doing this, maybe easier in the long run, which is to say, how does nature do it? Well, what nature does is it relies on tricks like fractality or self-similarity to create these complex structures where you have almost repeating but not exactly repeating structures on different length scales. And that adds a lot of complexity to the problem just by itself without you having to deal with 100 ingredients. And I'll come back to this in a few slides and will hopefully show you that that's exactly some of the physics that happens in quasicrystals. And it sounds like my microphone is switching on and off the whole time, but it's okay? Okay, good. Okay, so let's dive right in. What is quasicrystals? And let me start in 2D. In condensed matter 101, probably all of you have heard about the crystallographic restriction theorem. If you have a periodic crystal in 2 dimensions, you can only have 1, 2, 3, 4, and 6-fold rotational symmetries. And when you think about this in a geometric fashion, it makes a lot of sense. If you have a 4-fold symmetry, you naturally get a square. If you have a 6-fold symmetry, you naturally get a triangle, and you can tilt the plane with triangles. If you think of an 8-fold rotational symmetry, say this is your lattice constant, then an 8-fold rotational symmetry means you can make a rotation of 2 pi over 8, again a rotation of 2 pi over 8, and you end up somewhere that's pretty close, but not exactly the origin. So this is not commensurate. So what you have done now is, starting from 1 lattice constant, you have kind of created a smaller scale. And of course, this process can be repeated ad libitum, and you get smaller and smaller and smaller scales, telling you there cannot be a period in the system. So we understand just from simple geometry, if we have a different rotational symmetry than this one, we cannot have crystalline periodic order in the way we understand it. And for almost a century, people believed that that means that the only thing you can then have is something amorphous, no order, nothing special, boring, like a class maybe. But then came Dan Chestman in the 80s, and they showed these pictures. They took electron diffraction of this kind of material, and they saw, okay, first of all, there's very well-defined, very sharp Bragg peaks, which means we must have long-range order, because a sharp structure momentum space means a long correlation length in wheel space, necessarily. At the same time, if you can count, you have a 10-fold rotational symmetry around this axis. So that's impossible, that's forbidden. And there was a long debate, is this real physics, or is this just an experimental artifact that they maybe have twinnings or other crystallographic problems in the preparation of their samples that it's just an artifact of bad science. And the debate really went on repeatedly for a couple of years. Mathematics, at the same time, they were already far ahead of the game. They knew of things like a Penrose tiling, where you do not have one unit cell, you have two types of tiles, like the fat blue ones and the slimmer white ones, and you have a certain set of matching rules, how you have to put them next to each other. And they could show mathematically already decades earlier that these structures create self-similar fractal structures. Self-similar here means that you can, say, take this area consisting of a few tiles, replace it with one bigger tile, and then you get the same structure back just on a bigger scale. So there is a self-similarity built in here, there's a totality built in here, and you have structures where you have, for instance, in this case, a 5-fold rotational symmetry together with long-range order. So it's possible, it was recognized, and then got a Nobel Prize in Chemistry in 2011 for this work. So we have structures which are non-periodic, but nonetheless long-range ordered. And they actually occur also in real materials. Here's one example of a dodecahedral quasicrystal. And most of these examples so far have been man-made. But they have found one actually in the natural world. This is like a piece out of this material, which is kind of a natural occurring quasicrystal, which is found in one meteorite. So this stuff exists, but maybe not in our world. Could be interesting. You look at this and you say, is this periodic? It looks kind of ordered. It looks like it's ordered, but it's kind of hard to figure out what the period is. And why is this so hard? You see that you have a couple of axes here which are clearly identifiable, like this one, where all of these rings are aligned along this thing. And you have 10 of those, so the system is a 10-fold rotation, so it cannot be periodic. It can never repeat itself. And these structures are well known also in photonic systems. They can be created in photonic crystals reasonably easily, or also now this year they also came out in twisted bilayer graphene, where you take graphene, take the two layers, rotate it by 30 degrees. So out of the 6-fold, you get a 12-fold rotational symmetry, and then you can show that this kind of actually matches nicely with these kind of structures. So they are getting relevant. They are getting very relevant. But are they also really that complex? Can I prove that? Well, kind of. This is a paper in Nature from 3 years ago. Toby Cubitt, David Perez-Garcia, and Michel Wolf. And what they showed is that a many-body system, in principle, is very hard. It can be undecidable in the Turing sense, meaning the spectral gap problem. So the problem if I make the system bigger, 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 will all spectral gaps close at some point, the system becomes gapless or not, is in principle an undecidable problem, or can be an undecidable problem, which means it's very hard, very complex. And the interesting part in here is what they say is the proof of this combines Hamiltonian complexity techniques with aperiodic tilings. So it's kind of like a lattice Hamiltonian, but at least the proof they use does not work on a periodic lattice. It actually needs this aperiodic tiling with these extra complexities that come in. Now, one could, of course, say just point that their proof requires this aperiodic tiling does not mean that a periodic tiling could not have given the same thing. That's true, but at the same time, all of the things we know from RG and so on, we would expect that in a periodic system at some point you get into a scaling limit where nothing happens. So that's maybe enough motivation of going into these crystals. A second piece of motivation is coming from a different way of how you can create them. Another way how you can create something quasi-periodic is the so-called cut and project method. Here it's now seen for a 1D. So you start with an ordinary 2D crystal, a square lattice in this case, and then you take a slice out of this under an irrational angle, and everything that lies within this slice you project down onto a line. And if this angle is irrational, then what you get here down here is a so-called 1D Fibonacci chain. So it's also a structure that's long-range ordered, but it's never periodic. It's quasi-periodic. And the interesting thing about this is that the structure inherits a lot of properties from this two-dimensional parent. In particular, what they could show in a photonic context, or the Silberberg's group in Zurich, amongst others, is they could show, for instance, in a 1D photonic quasicrystal, that it's characterized by first Chern numbers because it inherits the topology from the 2D parent. So they have hedge states, charge pumping, all of the things that you would expect in the 2D system. They can see a 1D system, which is not periodic. And then they had an theory proposal that if I take a 2D photonic quasicrystal, that actually can inherit the topology from a 4D parent, so I can hope to take a 2D quasicrystal as a picture in the 4-dimensional physics. And that's kind of what we're now trying to do. So keep this idea of cut and project in mind, and then think about the simplest possible crystal in 4 dimensions. Simple cubic, hypercubic in 4D. So you have X, Y, Z, and let's call it W as the 4 lattice direction. And then you say, now I take this and project it down into 2 dimensions with the following matrix. X and Y, I just project along X and Y. And then the other 2 directions, I project along the diagonals. If you want to see a picture, if you take a projection from 3D to 2D, that's just a simple isomeric projection that you see all the time when you look at computer graphics. So here is the cube in 3D with the 3 direction, x, y, z, let's say, and you see it projected down into the 2-dimensional plane. So let me now just add the 4th dimension and project from 4D down into 2D. So you see we have now x, y, z, and the w direction, and you can already see that what naturally occurs here is this octagonal structure. If I take this 4D system and project it just down along this direction. If you stare at this picture long enough, you start to see different 3D cubes rotated, translated along the 4th direction. If you don't do it, have one and try again. Okay, so how can we create this kind of structure in the lattice, in the lab? That's actually rather easy. Because if you think of time reversal symmetry, it means we also need the other 4 vectors. So we need in total 8 lattice vectors coming in here. And that means we need 4 laser beams and the 4 retros. So we have these 8 beams in the plane, and they interfere. It's obvious that the structure is not disordered, because it's just created by 8 laser beams. There's no randomness coming in at no point. If we can take pairs with slightly different frequencies, so there's no cross interferences, it's also very, very easy to build, because if there's no cross interferences, we don't need to stabilize the individual fibers. The only thing that needs to be stable is the distances to the mirrors, which is roughly the same, say, as we have in ordinary square lattice. So it's straightforward to do. But is it really a quasicrystal? It's just a few interfering laser beams. This must be periodic. And the answer is no, it cannot be periodic, because it is 8-fold symmetric. And 8-fold symmetry is forbidden by what we said a few slides ago. Okay, so how can we probe this structure if we build it? How can we see we use 8-fold symmetry with our atoms? And the idea that we use here is like the same technique that people use for decades now to characterize their lattices. It's just a 2-photon transition. It's to say, if I think of my BEC sitting with some momentum, or an atom with some momentum, it can absorb a laser beam from a photon from one laser beam, go into the excited state, absorb the momentum of that photon, and then emit the photon into the counter-propagating beam, the one with minus k. And then what I do is I couple p to p plus 2h per k. And this is a standard Kapitza-Dirac diffraction that we all do in the lab all the time to characterize our lattices, and typically we get pictures like this. If we have the original BEC, we do a time of flight picture, we just see the peak in the middle. If we have a short pulse of this one, that the atoms can like absorb a photon from the left and emit to the right, they go here. They do it twice, they go here. They do it in the other direction, they go here and go here. And this is actually something that also the Price-Gatways group, Bernard Champagne, is now using, and really saying that you can think of this as a synthetic lattice in momentum space. So these are your lattice states now in momentum space, and you have hopping from one to the neighbor by one of these 2-photon processes. And if you want to have an analogy with optics, you would really say this is just, optics, this is really just Kapitza-Dirac diffraction. If you think of this in the quantum many-body sense, you would now say that if I take a BEC, I illuminate it with such a lattice pulse, it's like a quantum walk on this synthetic lattice. I have the synthetic lattice. Initially, everything is on the central side, p equals 0, and then I can hop to the neighboring sides by doing these 2-photon exchanges in momentum space. And here's a picture from Price's group. This is a initial state. This is now in 1D if they have a certain pulse duration where the system has now expanded to some directions, and they can either follow things nicely as a function of the pulse length. You really see a quantum walk in momentum space. We can do this now also in 1 dimension. This is our picture. Or in 2 dimensions where we say we have 2 of our 4 lattice beams on. So we have a square lattice and you get a typical square picture. Or we can do this in what we call 3D and 4D, where you have 3 or 4 lattice beams on. And why do we call this 4D? Let me explain in some detail. We call this 4D because it's like what we did said in the previous slide. It's really the projected version out of a 4-dimensional lattice. If we think of the fractality, this we can see maybe if we follow the peak around in time. Say we start with our BEC at 0 momentum. And then we say do a weak short lattice pulse, which is just enough that atoms can go to the first order diffraction. So they can do 1 2-photon hop into a neighboring lattice site. And because of the 8-fold symmetry, they can now reach these 8 states. Let's say they reach this state. Now starting from this one, they can of course in the next step go again in all 8 directions. So they can go back, they can go further, or they can go up along the diagonal here. If they go up along this diagonal, we do it again, 8 new states, and you see for instance that they can reach this state, which is now much closer to the origin than the first order peak was. And of course, I now just showed one example. This is all 8-fold rotationally symmetric. So out of this initial octagon of states here, we get like in third order another octagon here, which is actually smaller in size. And indeed, the scaling here is just the silver mean, 1 plus square root of 2. It's just given by the geometry. So we have a structure that is self-similar, because around each point we'll always have this whole series of octagons, and we actually now can have our systems doing a quantum walk on this fractal structure. If we now go for like third order, fifth order, sixth order, we can reach all kind of states. In here we get like a denser and denser set of peaks. In fact, you can think of this a little bit like the knight moves on a chessboard, where you cannot jump to your nearest neighbor, but you have to go like 2 to the right and then 1 up or 1 down. So if you want to reach your neighboring point, you have to go first this step, and then that step to come back. But now it's kind of a fractal chessboard because we have a dense set of all of these momentum classes that we can eventually address. So here's some pictures. After 1 microsecond, we have done 1 hop. We're in the first order. After, say, 3 microseconds, we can now do third order peaks, and after 6 microseconds, even higher order peaks. And if I now zoom in onto this, this is now something where you can see with the red bar here, this is the first order peaks, the first order octagon. And then this now is something, a third order octagon, where you have to go first this, then diagonally up and diagonally down to reach this point. Or you can go from here and then, for instance, up to, I guess it's this point, and then down to this point, how you can reach these third order points. So you can really see this fractality coming in. And if we now take slightly different parameters, we can get something like this, where we have even more peaks to see. And the scale by here is no difference. This is the first order peak, so we can see up in here is up to the 10th order peaks. We can see as how they're slowly filling in and filling up the plane. And for the experts, these are now pictures done with potassium-39 at the Feshbach resonance, because in order to have this good high resolution in momentum space, you really need to take out all of the interactions. Otherwise, the collisions in momentum space will mean that you have a billion of scattering spheres, and everything just becomes a mess. The peak height is related not only to the order, but it's related to the full dynamics. I can show you in a minute. Right, okay, so let me come to this. Just saying, okay, if you have a pretty complicated system, everything is nice if it's well aligned, but there's always Easter eggs to be found if it's not well aligned, or even an Easter bunny. So here's now some quantitative analysis of this. What we now do is we peaks 0th up to 7th order here, where the order is really the graph distance to the origin. So you take your coordinates in 4 dimensions, take the absolute value of them, sum them all up, and that tells you which order you're in. So this is now for a 2-dimensional lattice, or an ordinary square lattice, and you can see an oscillatory pattern. You see that the wave packet first starts to spread out over the first order, second order, into the third order, but then it turns around and comes back and rephases into the 0th order. And the reason for that is perfectly easy to understand. The reason for that is that if I have my potential lattice from here to the next orders, to the next orders, to the next orders, of course I also have the kinetic energy of those peaks to take into account, which is basically a harmonic trap in momentum space. So therefore what I can do now really is I can say, okay, this is just a quantum walk in harmonic trap. My wave packet starts in the middle, it oscillates outwards, but then it has to come back, and that's all we can do. Because all of the peaks that we go to, we always have to increase this distance, so we're walking up the hill. If I, on the other hand, think about the same thing in 4D, I can do something where I start from here, then go up, then maybe go here, then maybe go here, then maybe go here, and so on. So I can kind of oscillate around the middle point without ever having to go very high up in the potential. So I should expect that these kind of paths are possible, and indeed they are. So you can see if you do this in the 4D case, where all beams are on, actually population goes higher and higher and higher up, and this is really like a Lieb-Robinson bound, if you want, in the synthetic dimension, in the synthetic lattice momentum space. You have ballistic spreading of the wave packet in some directions of 4-dimensional space. In some directions, the system gets reflected. That's why you see kind of some stuff appearing back here, because if it chooses to always run up the hill, then it has to turn around. But it chooses a path like this. There's no reason for it to ever return to the origin. So we have, and if you think about this mathematically, because we have a dense set of all frequencies, there's no full recurrences. The Poincare time would really be infinitely far away here. Okay, if this idea of having this quantum walk and this ballistic spreading, at least for short times, is really valid, then I should be able to plot the RMS momentum width as a function of the lattice pulse and should follow these curves. And here the lines are single particle theory, and that actually works very well. If I think about very short pulses, the Fourier width of my pulse is so big that I can fully neglect about this kinetic energy. So it's just a ballistic expansion in a homogeneous 1, 2, 3, or 4-dimensional synthetic lattice. And the neat trick about this is if I think about Z to the D, the hypercubic lattices, if I think just the RMS width that I should get, so the square root of kx squared, ky squared, kz squared, and so on, it should just scale as the square root of the dimension. Because all of these 4 directions are orthogonal, so the system separates in 4 1D problems in this 4-dimensional space, if I don't have kinetic energy. Which means I should see a nice rescaling with square root of D, and indeed, if I rescale my RMS widths with square root of D, I see here for the first parts really a nice linear expansion, which is universal with the function with number of dimensions. So indeed, it matches very well. The deviations here at this point, they come in when the Fourier width of the pulse gets smaller, such that kinetic energy starts to play a role. So to go further here, what we now have to do is we have to go to pulse sequences, where we hit the system with like a whole sequence of pulses and explore this 4-dimensional space quite a bit bigger. Okay, let me, for the last 50 minutes or so, switch gears completely and talk about localization. Many-body localization is, of course, something that we have done a lot of work over the last couple of years. And I guess you're all familiar with the main concept, the idea that if you have a disordered potential, things become localized, and they can stay localized even in the presence of interactions. And it's a very interesting system because thermodynamics starts to break down. It's a little bit like what, thermodynamics starts to break down. And the typical picture that we've shown for like 5 years or so now was this picture, this phase diagram, where we said, okay, if you have a sufficiently disordered system, you have non-ergodic dynamics, which you can see, while for a sufficiently clean system, you have ergodic dynamics. And we always had this point here that the transition from extended to localized was happening at delta over J2, at a certain particular strength of the online modulation. And that was due to the fact that we were not using really a disorder potential there, but we were in fact really using a operion model, so a one-dimensional quasi-periodic model. We were just saying that, okay, when you think about this on short enough distances, quasi-periodic looks almost the same as random. It's only when you go to very large distances you see that, okay, wait a second, there is really some long-range regularity to this. In particular, that we looked at, that we always used there for the single particles, was the one-dimensional operion tree model, where you have the hopping to nearest neighbors, and you have the sinusoidal modulation of the on-site energies. And this one is interesting because the sinusoidal modulation is with an irrational beta. And I was pestering for years the theorists about, okay, what happens here really? How should this transition really happen? And of course, nobody could say anything for interacting particles. That's too complex. I fully understand. But I was also asking, what happens for single particle? How does the single particle localization look? Is it like typical critical exponents? Do we know these exponents? What's going on? Nobody could really tell me the answer because nobody was too interested. So we decided with a student, Attila Csabo in Cambridge, to look at this ourselves. And what we found is actually rather interesting, so I wanted to just give you a flavor of it. The key to understanding all of this is really this irrational number B. And every irrational number you can express in a very good and meaningful way as a string of integers in a so-called continuous fraction expansion. Let's assume that your number beta is between 0 and 1. Then you can say it's 1 over a whole number plus a little epsilon, plus some beta 1, which is like the part that makes it incommensurate. So it's roughly 1 over n1. And then you can say in the next step, okay, it's roughly 1 over n1 plus 1 over n2, again, approximating this with a whole number, and then again, the little rest that remains, and so on. That's a way how you can systematically approach any irrational number in like the most strongest converging case. So when you think about this now, what it means for your lattice period, the black dots here are your lattice sites. And let's say we have a beta where 1 over beta is just a little bit bigger than n1, say in this case 4. So what we can do in the first instance is we can say, so this is the real quasi-periodic modulation, which is incommensurate, the black line. Instance, let's assume that it would be periodic with period n1. Then we could do diagonalization of the system, would get 4 bands in this case, take the lowest band, take the Wannier functions from the lowest band, and they would live in all of those minima here. That's the first approximation. Now in the next approximation, what we would say is, okay, because you get these shifts here, which means that this point and this point are not fully equivalent, and we get kind of the green curve, like a next iteration, now a new longer range quasi-periodic modulation, which tells us this is now the errors that we did in the first case. And you can see how you can do this one ad infinitum, always going to better and better approximations. And what you get out of this is you get longer and length scales. The first length scale you get is n1. The second length scale you get is of the order n1 times n2. The third one n1, n2, n3, and so on. This goes on forever. And it's controlled by this number beta. And this is, of course, very interesting because it tells us that these quasi-periodic systems really have these new structures, even in Hamiltonian, coming in at all length scales. You can never say, okay, now I'm done, now nothing happens anymore. There's always more structure to come. and the structure is controlled by the next exponent in this continued fraction expansion here. So we went on, we said, okay, what happens now if we look at the approach to the critical point? Critical point right of here, and then this is the curvature of the lowest band, just one metric to see how the localization transition happens. And here's 3 different betas. And you can see, okay, this approaches the critical point, kind of among friends compatible with a rough power law with some modulation around it. But the point is that for general typical power law, this is just a power law because these continued fraction expansions are periodic. So you see here we have something that's 2,6 periodic, here something that's 6,2 periodic. So these two curves are almost the same, just phase shifted with respect to each other. And then if we start with the first other coefficient here, then it's kind of an offset. So there is cases where you can say it's like an ordinary phase transition with a critical exponent and a power law approach. But interestingly, if you, for instance, take now these curves here, the blue line is beta 2 periodic. This is actually the silver mean, the one that we use in the 2-dimensional case. Then you really have a nice power law just coming on here. But if you take a different beta, where say the first 5 coefficients are all 2s, but then it turns into 6 periodic or 8 periodic, then if you're away from the phase transition, it looks like you have the same thing, but then on approaching the phase transition, suddenly this power law changes, or does something totally different. And of course, for a generic beta, where these ends do whatever they want to do, there is no power law. And this makes a lot of sense when you think about it physically. If you say I have a system of a length 1,000 lattice sites, then of course I will never see the 20th or 30th decimal of beta. I only see the first 5, 6. And indeed, when you look at the correlation lengths here, only at very long correlation lengths, very close to the critical point, all of these deviations start to come in. So it's kind of funny. It's like the closer you get to the transition, the less universal you are. There is another type of universality here. That means that really this beta is important, but the precise Hamiltonian is unimportant. You can also put some modulation on the hopping, or you can take a continuum model, you get exactly the same behavior. It's just controlled by beta. And at that point, you can either deviate a lot and say, I do number theory now and try to understand the hidden meaning in these betas, or you can say, okay, this is good enough for us. Let's go on and do something else again. So we are physicists, so we do something else again, and we now say, let's go to the 2-dimensional potentials and ask what is the localization in there. It turns out you can do exact diagonalization for a single particle. And if you take our quasi-periodic potential that we just had with the 8 lattice beams, we ramp that one up. And then as a function of this lattice beam, there's a localization transition from a delocalized state at a lattice depth of roughly 1.8 recoil into a localized state. And if you do the calculations, it turns out you need to take quite a few generations in the numerics into account in your momentum state basis in order to get a good approximation of this very sharp transition. So how can we see this now in the experiment? And here there was something that's actually a new way of looking at localization in the experiment and looking at this transition, which I find rather intuitive and also rather instructive. So the idea is, let's start outside of the lattice where our BEC will just be a plane wave, e to the ikx where k is 0. If I now think of ramping up a periodic lattice, so I'm not localized, just a periodic lattice, then this will turn into a Bloch wave. So it's still a plane wave, but it's now modulated with a lattice periodic function, which basically means I can ask meaningfully the question, how fast can I go from here to here? And the answer is, when I think about my synthetic lattice picture, the Bloch wave, the ground state of the system with a certain coupling will be like some state is delocalized of, say, the first 3 or 5 of these orders. So I need to have time for like 2 or 3 of these hops in a synthetic lattice in order to reach this ground state adiabatically. And then, of course, I can also come back. So you can probe this. You can say, okay, what happens if I take a sequence like this where, as a function of time, I ramp up to a certain lattice depth and then ramp back down. And then I ask something akin to this return probability that we heard earlier, how much of the system at this point will still be back in this plane wave. If I'm not adiabatic, I will have created excitation in second excited band. But if I'm getting slower and slower and slower, I get more and more adiabatic, and I can get the time. So here's data for a 2-dimensional lattice, periodic lattice at 7 recoil lattice depth. This is the 0th order, the original BEC. And you can see this typical oscillating pattern. Of course, if the lattice pulse is 0 length, then we've never done anything, so it means everything is just stays in the BEC. And then it deviates a lot, comes back, and there is an oscillating pattern, which has to do that you have this just a few discrete frequencies in your spectrum, but then on timescales of something like approaching 100 microseconds, now really everything is adiabatic and everything is in the ground state, and the higher orders here, first and second order, are fully empty. This makes sense, and this actually happens very, very fast. It happens much faster than the timescales we typically use to load into a lattice, because this is the assumption that you have a homogeneous system, no trap, and no interactions. But fine. Now we can say, what happens if I have a localization transition? What happens if at some point instead of a Bloch wave, I have to have this localized wave function, which is exponentially localized at one point. Then you can intuitively say, argue that this must take a very, very long time, and you can argue this in two ways. First way is to say, just thinking about transport of particles. If you have an infinitely big system, constant density, and now this particle needs to localize to this point, that means a part of the wave function has to travel from there to here. And if I want to go back down, it has to travel again the other way. Which means in the thermodynamic limit, the timescale for this obviously must diverge. So at the lattice depth, this adiabaticity timescale must necessarily diverge, because it requires long-distance particle transport. If I think in my idea in the synthetic lattice in momentum space, I get the same story. I started with a localized state, but now I have a delocalization transition, where I have to go to very, very high momentum orders, which requires many hops. So the same story. Instead of from wide to narrow to wide, I now have to go from narrow to wide to narrow. But the same story, this timescale should diverge. And that's actually a very neat idea, because now we can have a look at what happens in the experiment, and we indeed see that, okay, this is not experimental. This is the number of particles remaining in the BEC after this ramp for different lattice depths. If you look at the black curve here, that's 1.5 recoil, that's below the localization transition. And okay, we can deviate a little bit away from 1, but then everything is basically back in the BEC for very long pulses. If on the average we go for 2, 2.5, or most drastically for 3 lattice depths, we get a very different behavior. We get something where most of the particles do not make it back into the BEC. They get excited, and very confusingly, I get something where if I try to become more adiabatic, so I go slower, 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 it just gets worse. So this curve is not approaching an adiabatic limit, it's kind of approaching the opposite. And that has to do with what happens here with these very long paths. If I give the atoms now a lot of time to explore the whole system, to make these very complicated loops into, say, the 20th, 30th, 50th, God knows how much orders, then of course they have very many ways that they have to retrace. So the more time I give them, they spread out over more of these momentum bases, and the harder it is for them to come back. Hence, I get something very unintuitive, which, by the way, you also see nicely in the theory. I get something very, very unintuitive, which basically tells me that I really want to get lost in this space. I don't want to come back. So I'm far away from normal adiabaticity. And it's actually a nice timescale for localization. This is kind of compatible with the critical point being at around this 1.8 recoil. And now my last slide, more or less, very quickly, is that it becomes very interesting, of course, with interactions. We can do the same thing, exactly the same experiment, now also with an interacting BEC. What you see here is the scattering length, and what you see here is the BEC fraction that comes back into the ground state. This is for one of those pulses, very long one, reasonably deep lattice, where you had everything, almost everything excited away from the BEC for non-interacting particles. But if I now switch on repulsive interactions, you can see the condensate fraction grows a lot, which means the system wants to be more adiabatic, wants to stay closer to the ground state if it's interacting. And I think when you think about this now in this two-dimensional or even higher dimensional space, you get a picture that's very interesting, because it's the opposite of what you would expect for fermions. You would really expect that for fermions, of course, the ground state will be very easy to localize, and it becomes harder to localize excited states, because then you have to fight against thermal energy. For the bosons, on the other hand, it looks like the other way around, that thermal bosons will be as easy or complicated to localize as thermal fermions. But if I now walk towards the ground state, I start to have superfluidity coming in. And superfluidity, of course, one would expect to counteract localization, and we really seem to see the fight between these two energy scales, between these two processes here. Okay, but this is pretty preliminary. We hope to have a lot of nice conversations about this during this week. And with this, I'm basically at the end, and here's my summary. Thank you very much.